Hey guys, what's the crack? Nice to see you're all at summer school. How's all feeling? Saw a lot of you talking about entrance exams for universities. How are we feeling about our exams? How are you feeling about how did year 12 go for you guys? So was it Saeed? He kind of stopped talking, singing a drop in it. That can't be true. You wouldn't be doing summer school physics, would you? You'd be doing something else. You'd be like, if you're already done with it, you'd already be tapped out, wouldn't you? So we'll just give it like a couple more minutes and then we'll start. So we'll just give it like a couple more minutes and then we'll start. So we'll just give it like a couple more minutes and then we'll start. Sorry. I tried to put YouTube up with it. I just cancelled it. I don't think that's a thing. I haven't learned that tech yet. Hopefully that the two voices there is gone now. Yeah, and someone asked before what course we're doing. So someone said it's kind of like an overview year 13. Yeah, that's true. So it should be grand for whatever course you're choosing to do. Whatever course you are doing. So like AQA, OCR. But I will be focused on AQA. And if you choose to do the courses, and hopefully you will, the one that I'll do all year, so the year 13 one. So I will be teaching the whole year 13 spec alongside your teachers teaching it to you. But that will be, yeah, mainly focused on AQA. So like some people said, there is some overlap between OCR and through the year, it's fine to do a bit of both, but coming up to your exams, because there's different parts on different specs. So for example, everything on paper one for AQA physics is not the same stuff that's on paper one for OCR physics. Although you do get tested on everything, if that makes sense to y'all. Okay, so we'll just start in about a minute. Yeah, for BTEC, you don't have to know as much in-depth content, but there is a lot of overlap. So, I've got I've got the TikTok and Instagram accounts. So if you have a course specific question, so say you want to know how much overlap there is between a BTEC course and what I'll be teaching, if you just send me a message on either TikTok or Instagram, and then I can show you the links and the specs, send you a message back. It's probably the easiest way to go into specifics about cross links in your courses. Yeah, so the one that's through the year, the one that's like alongside your teaching, yeah, you do have to pay for that one. But again, it's like much cheaper. That's why this company is set up, right? It's because I don't know if any of you all tried to get a tutor last year, but I used to be a tutor for physics and the going rate is like 70 quid an hour. So this course is trying to help everyone out. So like it's a lot more fair. Because I don't know about you guys, but when I was your guys' age, my mom would have had a heart attack if I told her a tutor was £70 an hour, right? Okay, so we'll just start in another minute. Are any of you all from the same school? Ah, you like my accent? Thank you. I was actually just talking to someone else there about that a second ago. So my accent, because I've lived in England for quite a while, is like tapered down quite a bit. But because I've been hanging out with a lot of my Irish friends recently, it's kind of like starting to come back. But you're from Blenheim. That who is Free Ninja? That's the school I was teaching at. Who are you? FYRE Ninja. Okay, so we're legendary. Thank you. Yes, we are. Kitans, I'll get back to you in that hot sec, if that's all right. At the end, we'll go over that if that's okay. Or again, I can talk to you about it separately if you want. But just a bit about me. So you've probably not seen me before unless you watch any of the Instagrams or Reels. But if you do want extra vision, the TikTok is great. The TikTok is probably the old way to call it. But anyway, I do like a lot of exam questions on there and things, past paper questions. So that's probably quite helpful. But yeah, a bit about me. So you know why would you even be listening to me, right? So when I was at school, so your guys' age, I saw some of you talking about doing 4 A levels. So I did all 4 as well. So you can see there, I did math, biology, chemistry, and physics. And again, I just love them, right? I just think sometimes you either have a head where you're better at English and you're better at languages, or you're just better at math. I just really like math and science. I just didn't know which science I liked better because I was a bit torn between medicine and physics. And then I just loved my physics teacher. We just went to really good lectures all the time, different universities. I went to one that was called We Are a Star. So it was like talking about how everything in our bodies, or all of our atoms, all of our molecules, all was born in a star at one point from a supernova. So it's the only way to get any heavy elements. I just thought that was fascinating. And I met a lady one time where she had 2 watches because she worked with the rover on Mars. So she had a watch for the time on Earth, and then she had a watch for the time on Mars. And that stuff, I just loved it. So that's why I went into astrophysics. And your dad went to MSU at alumni. So you know the mascot, Go Green. Do you know Uncle Kebab? Do you know does he say that to you, Go Green? So yeah, so I went to MSU then because I was really into sports. And that's something I actually tell all the ones I teach, especially if you're going into your 13 year right now. There's been loads of research, and you're probably like, why is she talking about this when we're doing physics? But there's loads of research that the more sports you do, the more capacity you have your frontal lobe for memory. So it's actually really bad for you to go home from school and just study 24/7, because like you go home, there's about like 8 more hours in your day. You're not going to study for 8 hours, right? You're going to be on your phone distracted. But if you have a sport, then when you actually study, you get back into it. You have more capacity for it. You're more willing to study. So I was really into rowing. I don't know if any watched it on the Olympics. Did anyone watch rowing on the Olympics? Do you know what it is? But anyway, I was really into rowing, and I got a scholarship to MSU. So yeah, so Uncle Kebab, me and your dad, we can have memories. So I went to MSU, which is in the States. And then after that, I went and did my master's in England. So I went to UCL, so University College London. And in planetary science, because I kind of got more interested in if there's life on other planets rather than just looking at stars. So if there's any of those careers or topics you're interested in, please just hit me up at some point and we can like chat about it a bit more if you want. Okay. So just to see what you guys know. So I know some teachers are quite different. Katan used to be a rower. What are you sculler? What were you? Were you in quads, 8s? But I know some of your teachers will teach this topic. So thermal physics, like for example, I used to teach it at the end of year 12 after you do your mocks, just to get you a head start into year 13. So probably quite a few of you have already learned this topic. And some of your teachers probably won't teach it then until you go back at the start of year 13. So it might be a revision for some of you. It might be a reteach or a quick recap for some of you. And then that's kind of how this course will go. So we're just going to go through all the year 13 topics, like a 50-minute lesson, an hour lesson on each one, just to give you a quick intro. So when they do come up in your year 13, you have a bit of background, right? Because there's nothing worse than when your teacher does a new topic and you're one of the people sitting in the class and you're zoned out for like 30 minutes, right? Because you missed the 5-minute intro at the start. You don't know what's happening. So I guess that's what this is for, just to help you guys get prepared for those first few lessons so that you never have to feel like that. 8s are messy, not if you've got a good set of people. Yeah, so thermal physics isn't EdXL. So all the topics we're doing over summer school are on all the exam boards. So EdXL, OCR, AQA. I'll just be taking it from an AQA point of view. So like how the equations look in the equation sheets in the AQA equation sheet. So yeah, all the topics do come up in all of the information we'll be doing in summer school will be in all of the exam boards. They just come up in different papers. So for example, this is a paper 2 content in AQA, but some of it comes up in paper 1 in OCR. And again, if you just want to message me on TikTok, you can send me a private message. I can show you the cross links between the specs and where they come up in different papers, if that would help you out. Year 12 content, we're not going to recap on this session. So we do recap it. If you choose to do the course through the year, we'll do loads of recap of year 12 stuff through the year with it. But there's a year 12 course that I'm doing alongside this. So I just had that lesson this morning. So if you want to join it, you're obviously welcome to. Okay, so do you want to have a go at this then? So first one is, what is the definition of internal energy? And I've got a picture there to hopefully help you out a little bit. So what's the definition of internal energy? So internal energy, it's the sum of something. You don't want to hopefully give us a go, right? Be brave, type the chat. So it's the sum. Minimum energy required to change state. We're going to come up to change state in a little bit. So thank you, Cordy, for getting us started. Total kinetic energy and thermal energy. It is brilliant. Carla, thank you. So that's just where we're going to get started there. So it's sum of, the only thing you have to say now before kinetic energy, and they underline this in the AQA specs, you have to say sum of the random distribution. So sum of the random distribution of the kinetic energy, I'm just going to write KE for kinetic energy, and the potential energy. So exactly what Carla said there, you just want to add these two words at the front. Okay, it's random distribution because it's a Boltzmann curve. So you don't need to know how to draw a Boltzmann curve, what it is, but basically what's on your x-axis is your energy, or you could say maybe speed of the particles. And let's say on your y-axis is the number of particles. So it looks, a Boltzmann curve, you might have heard of it before, it's kind of just that shape. So this is showing you the speed of the particles. So you can see most particles have a specific speed. Most particles have a specific speed, but there's quite a big range of speeds. So that's why we can't just say it's the sum of the kinetic energy. It's the sum of the random distribution, right? So right now, all the oxygen in my room, not every single oxygen particle will be moving at maybe 20 meters per second. There'll be some at 20 meters per second, some at 10, some at 15, some at 18, but the most of them will be moving at the 20, okay? Okay, so next one, what do we think has a higher internal energy? So now we know what it is, the sum of the random distribution. Which one has a higher internal energy? Do you think it is ice or liquid water? So solid ice or liquid water? Yeah, there is a cross link. So this topic does come up in chemistry a lot as well. So if you do chemistry, you'll probably quite like this topic. However, I last year was teaching two chemists. It was in my physics class. And I think because you get taught it slightly different in chemistry, it's kind of hard to switch from degrees C's to Kelvin. So we'll go over that quite a lot. Yeah, lovely. Thanks for popping in the chat. Yeah, Carla, Heba, lovely. Timothy, nice. Jessica. Yeah, fab, lovely. Yeah, fab guys, thanks. So the one that's got the highest internal energy is your liquid water, because clearly it's got more kinetic energy, because we know water particles, that's something from key stage 3, right? Solid particles only vibrate, whereas water particles can move over each other. So the water particles have more kinetic energy and they have more potential energy. So you've learned about potential energy loads, right? So gravitational potential energy is how far away you are from the ground. So the further you are from the ground, the more potential energy you have. So the further the particles are apart, the more potential energy there is. So we know in solids, they're all touching tight, whereas liquids, they're more free to move. So that's why they've got both more kinetic energy and they have more potential energy, which is why they have a greater internal energy. Okay, next one is, how do we increase something's internal energy? So how do we increase internal energy? Sheriff, you're waiting on year 13 results. So it must mean you finished year 13. So what, are you in this course just in case you have to repeat? Yes, nice. Justy Klein, beautiful. We want to do work done, right? Nice. We want to do work on the substance. And the two ways we can do by work is either by doing heating, good job. So we can do two ways to do work. We can either do it by heating, or what was in the chance. Yeah, good job. So work done on the substance, and we can do that just by heating up. Yeah, nice. Okay, next one is, do we know the difference from 0 Kelvin and 0 degrees C? Ah, Sheriff, you're in the crash course. You're here for fun. You're just trying to, well, I suppose that's actually really smart, because if you're going into uni, you don't really want to go in your first week and not have a clue what's happening, right? You kind of do forget everything over summer. Yeah, lovely. So you've done chemistry, you probably know about it. So does anyone know what's special about 0 Kelvin? What do we call 0 Kelvin? Yeah, right. So a lot of times you're probably very used to doing temperature in degrees Celsius, right? So we say like 0 degrees Celsius is what water freezes, 100 degrees Celsius is what water boils at. But in chemistry, in physics, you have to use Kelvin. So Kelvin is your SI unit for temperature, so your international unit temperature. And we use it because exactly what Jessica said there, 0 Kelvin is called absolute zero. So 0 Kelvin is your absolute zero. So what that means is the coldest we can get right now. It's the coldest that thing can ever be. So 0 Kelvin is the coldest something can be. When we try to put that in degrees Celsius, it obviously must be a bigger number, right? So 0 Kelvin is 273 degrees Celsius. Okay, like Dusty Klein put in there, it is, if you Google it, is exactly 273.15 is 0 Kelvin. We don't need to remember the 15 at all, okay? For your AQA and for all the exam boards, you just need to remember 273. So you need to know to get from Kelvin into Celsius, you always just have to add 273, okay? So that's what you just need to remember for this topic. So for this topic, we always want our final answers in Kelvin, and we just add 273. Yeah, good job. So, like someone said there, if I have 100 degrees Celsius and I want to figure out what that is in Kelvin, to go the other way, to go from degree C to Kelvin, you see that you subtract 273. So to go from degree C to Kelvin, you just take away 273. Oh, 0 Kelvin is the coldest something can be. Of course, sorry, I'm having a mind blank there. Now you're all going to hate me. Of course, the coldest something can be is not 273 degrees Celsius. That's like way above 100. It's negative 273. So you subtract 273. You're 100% right there. Thank you for popping it in there. I had a blank. Okay, yeah, so 0 Kelvin. Imagine the coldest something could be. I'm telling y'all, the coldest something could be is 273. You're sitting there thinking, what? My room's sitting at 25 right now. So yeah, sorry. So to get from Kelvin to degree C, you want to subtract 273. Apologies. So just to make sure we're good then, to go from degree C into Kelvin, you're going to add 273. So that's why exactly what Ayo put in the chat there, to go from 100 degrees C, I'm going to add 273 to get it into Kelvin, which is why it's 373 Kelvin. So we are going to practice that for this lesson. So I apologize again. I was just making sure you're all listening, right? All you chemists in there that learned this last year. Just checking if you paid attention. Okay, next one. What is specific heat capacity? What is specific heat capacity? What's the definition that hopefully you remember from your GCSEs? Yeah, Rehan, beautiful. The energy required to raise 1 kilogram of substance by 1 degree Celsius. So just change that slightly now that I told you it has to be in Kelvin. Specific heat capacity is the energy required to increase the temperature by 1 degree. Beautiful, Ruben. But remember, we have to specify the units now. Yeah, lovely. So from GCSEs, like we just said, it was always in Celsius. This comes up in AQA quite a lot as a definition. The way I remember the definition is to look at the equation, okay? So the equation on your data sheet, if you do AQA, is the change in Q stands for energy, equals MC times the change in theta. And theta stands for your change in your temperature, okay? So if I want to find out what C is, just the specific heat capacity, all we have to do is rearrange that, divide both sides by M times change in temperature. So specific heat capacity is the energy to change 1 kilogram of substance by 1 Kelvin, and you have to add now without changing state. Yeah, finish there at the end, beautiful, without a change in state, okay? So you just want to add that into everybody's answers there. So it's the energy required to raise 1 kilogram of substance by 1 Kelvin is what you have to say now. So it's 1 Kelvin without a change in state. Okay. Okay, so I'm just going to rub out this bottom bit so we can do question 6. Question 6 then, can you tell me what the specific heat capacity is of that can? So pop in the chat. What's the specific heat capacity of that can? So again, if I want to find specific heat capacity, we've just got to do the change in the energy, that's what Q stands for, over its mass times its change in temperature. Yeah, you do, Zila. So for AQA, they have to have this in your answer as well. It's the whole thing. And AQA are really specific about their definitions. Okay, so hopefully you're thinking change in energy. We can see it there is our 32175 joules. And we're dividing it by the mass. Hopefully everyone's thinking I'm in physics, right? I can't have it in grams. It's got to be in kilograms. So that's my 0.33 times by the change in temperature. So it's 20 to 5. So that change is 25. So if I pop that in my calculator, just get my final answer. If someone, yes, thank you, Kitan, beautiful. The final answer then is going to be 3900. And the way to find the units is on top, I have an energy, which is joules. And then on the bottom, I have mass, which is kilogram. And my Kelvin, right? So just to make sure we're okay with that. If it was 20 degrees Celsius, changing to 5 degrees Celsius, minus 5, sorry, that total change there is 25. If I can put them both into Kelvin, so for example, to get that into Kelvin, I'm going to add the numbers up. So if I did 20 plus 273, that's 293 Kelvin. And negative 5 degrees Celsius, so negative 5 plus 273, is 268 Kelvin. If you look at that change in Kelvin, it's still got a change of 25, right? So because the change is still 25, that's why we can keep our units in Kelvin. So it's joules per kilogram per Kelvin. So joules per kilogram per Kelvin. Yeah, Jesse Klein, beautiful. Nice. Okay, so that's like a quick GCSE thing. And this is a little bit from your GCSEs as well. So just to recap, before we get into a bit more harder math. So hopefully you've all seen this graph before. So this is us looking at water, okay? So we know water changes state at 2 temperatures. The first change in state happens at 0 degrees Celsius, and the second change in state happens at 100 degrees Celsius, okay? So what we want to do here, the first bit is I can clearly see when the temperature, so my y-axis, when the temperature rises, that's when we know there's going to be a change in the kinetic energy, right? So here, below 0 degrees is a solid. So why it's a solid, and what I'm doing over time is I'm heating that solid up. As I'm heating the solid up, those solid particles are vibrating faster and faster and faster and faster, and I'm increasing their kinetic energy, okay? So here, we always use the equation that we just did about specific heat capacity. The change in energy is equal to the mass of the solid I have times the specific heat capacity of the solid I have times whatever that change in temperature was of my solid. And then as soon as I hit 0 degrees Celsius, those solid particles that we're touching and vibrating, now what happens is they undergo a change in state. So what happens is the temperature stays the same, so there's no change in temperature, even though I'm still heating it up. But the particles, they start to break away from each other. So what I'm changing here is the potential energy. Because you remember we said earlier, internal energy is the sum of the random distribution of the kinetic and the potential. So here, I'm increasing the potential energy. I'm breaking the particles apart. I'm breaking those intermolecular forces. Here, now it's a liquid. I'm heating my liquid up. So I'm going to use my equation again. Change in energy is mc times change in temperature. And then here, when it's boiling, the temperature doesn't change because what I'm using all that energy to do is to break those bonds. So I'm changing from my liquid into my gas. And that's why the line is flat. Because the line is flat and there's no change in temperature, we ignore this part. And that's why we can write that the energy is equal to m times L. You don't have to include change in temperature in your answer. Okay? Okay, so just again, because we said earlier about definitions, really important. So we said a minute ago, we taught specific heat capacity. Then for these parts here, where there is a change in state, we always use energy is mass times L, specific latent heat. So sometimes they'll ask you, what is the specific latent heat of vaporization? And the way I remember vaporization is that's when things are gases. Okay, so anytime you're talking about a gas, so say you're going from a liquid to a gas or from a gas to a liquid, you're always going to use the vaporization numbers. And that is, if I look at L, that's my Q over M. So that's how much energy I need to change state of 1 kilogram of the substance without a change in temperature. Okay, so just like the last definition, it's really important you include that little bit. And then specifically at fusion, which is right here, because if you think about fusing things together, you're joining them together. So that's always to do with solids. So this number we use when we go from solids to liquids or liquids to solids. And again, that's the amount of energy I need, change state of 1 kilogram of substance without, again, a change in temperature. Okay, so I just wanted to go over that to make sure we're okay to do some of the math. And again, just to make sure we're okay about specific heat capacity, you've all heard about it, but I just think it's such an out there concept. Just wanted to go over what it was. So the way I think is the easiest to understand is if I have pizza, right, and you want to cook your pizza, you put the whole pizza in the oven and the whole pizza is at the same temperature in the oven, right? The pizza maybe started in the freezer at like -5 and you heat it up to maybe 70. The whole pizza has the same change in temperature, right? The whole pizza has a certain mass. We're putting the same amount of energy into it. But when I lift the bread to take a bite, I might touch the bread and think, oh, that's grand, I can eat it. But as soon as I put it in my mouth, I'll burn my mouth because the cheese, even though it was at the same temperature, it was in the same oven for the same amount of time, the cheese has a different specific heat capacity. It releases its thermal energy at a different rate than the bread, right? So again, they both are in the same oven, the same temperature, but because they have specific heat capacities, the bread and the cheese store their energy differently. So that's why you might burn your fingers on the cheese. Okay, so just to get back into some math, if you look here, so I've got loads of different substances. I've got the specific heat capacity. Which substance do you think is the hardest to heat up? So looking at those numbers, which one would be the hardest to heat up? So which one would I have to put the most energy in to heat up? If you pop it in the chat for me. So which one of those substances would I need the most energy to heat up? So the hardest to heat up. Carl, thank you for going first. So do we agree with Carl? Timothy agrees with Carl. Uncle Kebab doesn't. So which one is the hardest to heat up? So remember, think about it. Specific heat capacity, if we rearrange it, is the change in energy over mass times the change in the temperature. Or specific energy is specific heat capacity, how much energy I need to increase the temperature of 1 kilogram of substance by 1 Kelvin without a change of state. Yeah, nice. It has to be water, right? Because we have to put in more energy to change state of 1 kilogram of water by 1 Kelvin than I have to do for mercury. So look again, water, I had to put in 4,200 joules of energy to increase 1 kilogram of it by 1 Kelvin. Whereas in mercury, I only had to put in 140 joules of energy to increase the temperature of 1 kilogram of it by 1 Kelvin. So that's why it has to be water here. Okay, what about the next one? Which one's going to be the hardest to cool down then? Which one is the hardest to cool down? Which one is the hardest to cool down? So remember, the definition is the amount of energy needed to change 1 kilogram of substance by 1 Kelvin. Amount of energy to change 1 kilogram of substance by 1 Kelvin without a change in state. Kai, you're on it. Good job, Zila. Good job. Yeah, that's a trick question. It is water again. I just want to show you that's how the definition works. So just to write the definition again, remember, it's the amount of energy we need, the amount of energy to change 1 kilogram of substance by 1 Kelvin without a change in state. So that's why it's still water. Yeah, nice. This question, we just talked about it before. It's fine if you keep it in degrees Celsius because it's a change in temperature. So even if we add 273 to both numbers, the change will still be the same. Okay. Okay, so what we're going to end tonight is we're going on to this question. Does anyone know what happens if we have 1 kilogram of aluminium at 20 degrees C and we put it in contact with 1 kilogram of silver at 4 degrees C? What's going to happen to the heat? What happens to the temperature of them? Or another example could be if I took my can of Coke out of the fridge and I left it in the room for a long time, what eventually has to happen? So if you think about it, if you take a can of Coke out of the fridge, right, it's really cold. Yeah, there's going to be heat transfer. Yeah, anyone mad? Thank you, yes. So what's going to happen is they're going to reach thermal equilibrium. Yeah, good job, right? Any lovely. They're going to reach the same final temperature. So it's really nice. So thermal equilibrium, thermal obviously stands for heat, thermal equilibrium. Equilibrium is just the same. So thermal equilibrium is the heat will change between the two of them until they become the same temperature. And that's really important because that's the math we're going to focus on next. Okay. Okay, so this one is just to understand why it's really important that. So let's say I've got my water here. We just looked at the graph earlier. So remember we looked at the graph and we're heating water up. There was 2 changes in state. Is all of the energy used to heat the water? What do you think? So if I know how much energy I'm putting in here from this Bunsen burner, is all of that energy going into my water? Is all of the energy going to my water? Do you think it's... So when we do our calculations to calculate specific heat capacity of water, we normally do the change in energy over the mass times the change in temperature. And what I'm asking is that change in energy, is that how I actually calculate the specific heat capacity? Yeah, thank you. Brilliant. Yeah, nice, Kelsey. Yeah, Carla, Kai. Improps, yeah, right? No. Good job. Kitan, thank you. Energy goes to the environment, and Ruben, even better, nice. So nice if we said about Ruben here. If you think about this, that gauze, you don't need the word gauze for physics, but as a gauze, that gauze there is between the water and the beaker. So when I'm heating this up, some of that energy is actually going into my gauze. Some of the energy is going into my glass that's around the beaker, right? Not all of it's going there. So the amount of energy I input is actually equal to mass of the gauze times the specific heat capacity of the gauze times the change in temperature of the gauze plus the mass of my glass. times the specific heat capacity of my glass times the change in temperature of my glass plus the mass of my water times the specific heat capacity of my water times by the change in temperature of my water. Okay, so in GCSE, when you did this, we just assumed that all of the energy just went into the water. But in year 13 physics, what you have to do right now is you have to think about there is some energy going into those other containers around. So you just have to take those into account when you do the math. Okay, so that's what we're just going to practice. So before we practice that, I just want to make sure you're all okay with equations. Can you give a go at this one? So it says, I've got a 2 kilowatt kettle. And it says, I want to raise the temperature of 800 grams of water from 20 Celsius to 100 Celsius. Sorry, that red hands at the top of there. Specific heat capacity of water is this number. So you're trying to give me a time, how long? So give a go in the chat. What is the final answer for time? And then do you think this is actually the correct time, or do you think it would actually take longer, or would it actually take less time? Yeah, Kat, it does. So for this question, I'm just saying, just use the water. And I just want you to tell me a time, and then you're going to comment, is that time a true time of how long it takes to heat that water up? Or would it take actually longer because you're considering the other components, or would it actually take less? So we're going to look at some questions in a bit where we actually look at where they tell you the other components. And the biggest hint is the specific heat capacity. If they only give you the specific heat capacity for one substance, you can only do it for one substance. And if they give you the specific heat capacity for the other substances, then obviously you know you've got to use the math for it there. Okay, so hopefully the first thing you're thinking is they gave me specific heat capacity. So the first thing I'm going to do is try to use that somehow. And then I'm thinking about how can I get something to do with specific heat capacity, which is a change in energy equals MC times the change in temperature. How can I relate one of these to time? Yeah, Ruben, beautiful. Kitan, beautiful. Yeah, flying on. Good on. So you get a few more people. So we're trying to figure out what is that time. So hopefully you're thinking the first thing I should do is calculate the energy. And you're trying to think about what equation should I remember, because you don't want to be looking at your data sheet for this, right? You only want to be looking at your data sheet for those questions that you're really struggling with. Because you know you got like 1 minute a question, right? So you can't be wasting this time trying to look through for all your equations. You should hopefully remember power is energy over time. And I was given a power there. So I know that 2000 equals some energy over a time. And I want to calculate time. So I must know energy from my specific heat capacity equation. So hopefully, if we're doing what everybody else did there, to find out what that change in energy is, we take the mass, and again, hopefully everyone's remembering it has to be in kilograms. So our mass times our specific heat capacity times by our change in temperature, which is 80. And when I do that math, I get a final answer of 268,800 joules. And then all I need to do now is take that number and divide it by 2000 to get my time. So to get time, all we have to do is 268,800 divide it by 2000. And I got the same answer as a few people up in the chat there. So Ruben, awesome. Timothy, awesome. Carla, beautiful. So you get 134.4 seconds. Okay. So hopefully this is a good reminder for everybody. So this is the equation you need to memorize. Okay. So just be something in your head all the time. You see watts and you're thinking, how can I relate watts specific heat capacity? I just know energies over time. Yeah. Kelsey, thanks for asking. It's because I gave you the mass here in grams. So to get from grams to kilograms, because mass in physics has to be in kilograms, you just need to divide it by 1,000. Okay, so it has to be in kilograms. Because remember we talked about our units earlier for specific heat capacity. If you look at the units here, you can see it has to be in kilograms. Kilograms to the -1. Yeah. Yeah, no worries. Thank you for asking. Okay, so now we're looking at is just going over these words before we look at a bit more complex math. So just to make sure we go with this equation, so remember we just looked at it, when there is a change in state, we can use that equation, mass times the specific latent heat. So what I've given here, you have a table with loads of different substances. I've given you the specific latent heat for fusion. So remember, fusion is anything, I think about things joined together, anything to do with solids going to liquids or liquids going to solids. And I've given you the specific heat for vaporization, and vaporization, I think of things being vaporized, it's got to do with gases. So we use this number anytime we're talking about liquids going to gases or gases going back into liquids. Okay. So the first one says how much energy, so what time of energy required to melt 4 kilograms. So I know the mass is 4. So I just want to figure out what L are we going to use here, and then give me your answer. So see, you can pop your answer in the chat. So what L am I going to use if I'm trying to melt gold? Melt gold. Ah, Ruben, straight on it. Nice. Anyone else? So just to help you out, so we find gold. Here's gold. I've got 2 different numbers I can use for L, either this one or this one. Because it said melting. Melting is me going from a solid to a liquid. So it's got something to do with solid, so it has to be this number. So I'm going to do 4 times 1.1 times 10 to the power 5 to get a final answer of 4.4 times 10 to the power of 5. And the answer for energy is always in joules. Yeah, the fusion one. Yeah, Miriam, brilliant. Nice. Okay, next one then is, how much energy does 500 grams of carbon dioxide gas need to absorb to turn it into liquid carbon dioxide at its boiling point without a change in temperature? So because again, there's no change in temperature, so I can just use E equals ml. What final answer? How do you pick, Zila? Yeah, so everyone have a go at this one. So again, how we pick is you have to look at the vocab. So you see it says melting here. So I know melting, I think about ice. Melting is anything going from a solid into a liquid, okay? And anytime you talk about the word solids, you think about things touching. So that's why we use the one for fusion. So fusion we use anytime it's solids to liquids or liquids to solid. And if something gets vaporized, you're probably seeing like movies, like in Marvel movies, when someone's been vaporized, they become like gas, right? They're in thin air. So vaporization is anytime we're talking about gases. So vaporization is liquid to gases or gases to liquids. 2.85 times 10 to the power 5. Beautiful. Yeah, Kitan, good job. Nice. So for this one, it says I've got carbon dioxide gas and I want to put it into liquid. So hopefully everyone's thinking I have to use the number here for vaporization. So I find carbon dioxide and I'm using the number for vaporization. So what I do is I have to check my mass. Remember, it has to be in kilograms. So 0.5 multiplied by 5.7 times 10 to the power 5. And I get a final answer there, which everybody popped in the chat, which is 2.85 times 10 to the power 5 joules. Yeah, Jessica, nice. Priscilla, beautiful. Priscilla is a lovely name. It's really nice to say. Okay, number 3. A freezer produces 1 kilogram of ice every hour. What is the minimum energy that needs to be absorbed by the water to do this? So hopefully you're thinking, well, I'll just go for this one. So energy, if I'm producing ice, I'm thinking solid, right? So what I'm going to do is I look at my water numbers and I'm looking at my solid numbers. So the energy there is whatever my mass is times 3.4 times 10 to the power 5. And my mass, it told me to use 1. It's just 1 kilogram. Okay. So this was just trying to get in the hang of how do we know which number to use? How do we know to use fusion? Sorry. How do we know to use fusion or how do we know to use vaporization? Yeah, beautiful. So 3.4 times 10 to the power of 5. Nice. Yes, thank you, Ruben. Yeah, we're assuming that no energy has been lost to the surroundings. No one's been dissipated. Okay, just to make sure we're okay what we've done, because with this question 3 here is the type of stuff we're going to move on to now. Okay, so just to make sure we're good, can you really quickly pop in what was our definition for specific heat capacity? And can you explain the shape of this graph? So these are the 2 things we've been focusing on at the first half an hour there. So it's your exam. You're sitting your year 13 exam tomorrow. You've got to write in what's your definition of specific heat capacity. What would you write? Yep, Timothy, spot on. So pop in the chat for me. What is the perfect full marks? Because you want to get your units in there too. Yeah, units, Carla, is beautiful. So how would you write that in words? Basically what I'm asking you. Pramat, no worries. You're coming in when we're starting the hardcore math, so it's a good time to come. Miriam, you're so close, but you wouldn't got your marks. Sorry, you got to change that degree Celsius. Rehan, so close as well. You forgot a sentence there at the end. Remember we said that they're really specific on your definitions. Ah, Kelsey. Happy days. Yes. Energy required to increase 1 kilo substance by 1 Kelvin without a change in state. That's beautiful. 1 kilogram, 1 Kelvin without a change in state. Ribbon, beautiful. Yeah. Here. So if I said it wrong. Here. Beautiful. Ah, A1 mad. Come on. Not Celsius. What are you going to write? Yeah, Jessica, beautiful. Cordy, careful, you're just forgetting a sentence there. Yeah, Priscilla, beautiful. Yeah, good job. So just put it in here. Remember, what I do is I look at my equation. So when we rearrange our equation, we get this. So what we're going to write is, it is the energy, because that's on top, the energy required to heat 1 kilogram of substance by 1 Kelvin, because remember the units have to have Kelvin in it, and then you have to say now, without a change in state. Okay. Okay, this one says, explain the shape of the graph, name the change in state and what happens. So part II is hopefully, let's say we start here and let's say we're adding heat. So what's happening at part II? Yeah, Miriam, you have to say Kelvin. Yeah, because of the units for AQA, right? So if you're at AQA, it has to be Kelvin. So change in state here, hopefully we're thinking is what? So pop in the chat to me, what change in state is happening here and what change in state is happening here. Hopefully you can look at the numbers and think what substance it is as well. And then if it's easy and you're looking for a challenge, because this is the math we're going to now, give a go at question 3. Yeah, lovely. Melting, nice. So it's our first change in state. So we only know there is 2 changes in state, right? Melting is one and then the other one. One of them's happening at a lower temperature. One of them's happening at a higher one. So it must be melting. And it must be, the top one then must be boiling. Thank you, Carl. Lovely. Top one has to be boiling, right? So boiling is your other change in state. Okay. And then we know this has to be for the substance water, because if we look at those numbers, I have the number 0 here and I have the number 100 here. So that's how we know it must be for the substance water. Yeah, nice. Yeah, or you can call it vaporization. Yeah, fab. So boiling's fine, vaporization's fine. You just cannot say evaporation, right? So completely get rid of that word. Evaporation is something different, and you learn about it a lot more in chemistry. Never say evaporation. It has to be boiling or vaporization. Okay. Okay, this one. So this is the type of stuff we're going to now. So this is just us getting intro to it. So it says calculate the energy needed to melt 5 kilograms of ice at 0 degrees C and then heat it to 50 degrees C. So what I'm telling you is I have a block of ice, and my block of ice has got a mass of 5 kilograms and it's currently sitting here at 0 degrees Celsius. I want you to tell me how much energy I need to change that ice into water. And then once I've changed it into water, I now want to increase its temperature to 50 degrees Celsius. So what's the total energy that I have to put in? So I've got in the chat. And your clue is always here, that they've given you 2 different values, okay? So your clue is there that they've given you 2 different values. So clue is giving 2. A few people giving it a go. So do we agree? Yeah, so I get a lot of the questions as always with me, it's going to be adapting past papers, right? Because it's the only way to learn is just do loads of past paper questions, repeat it. So yeah, a lot of the question we'll be doing is just past paper questions, just adapt it slightly so that you can see different examples of them all the time. So again, we've got ice and we're trying to change state of it, and then we're trying to increase its temperature. So I've got 2 answers that agree with each other so far. Does everybody else agree? Talish agrees. Beautiful, Talish. I've not seen you yet. Sorry if I butchered your name there. Here, lovely. Good job. Kitans, beautiful. JMB got the same. That's a lazy way to type in the chat. Oh, yeah. Okay, so hopefully we're thinking total energy. The first thing we said is going to be a change in state, right? So we change state. We know it's a nice equation. It's just M times L. The mass was 5, and it was nice because it's already in kilograms, times L, the specific latent heat of fusion, is 3.36 times 10 to the power 5. And then we also know that we've increased its temperature. So I have to use MC, change in temperature. So it's going to be 5 times, it's a water, right? Because we just changed our ice into water. We've got 5 kilograms of water right now at 0 degrees Celsius. And I need to heat that water up to 50. So I'm now in water, which is why I use my number for water. And the change in temperature is 50. So when we add those 2 numbers together, thank you, Kitan. Yes, of course it is. So we get 2.73 times 10 to the power 6 joules. Okay, so this is quite nice maths. We're going to do this quite a lot. Okay. So we're going to move on now. Okay, so we're going to look at this stuff now where you've got to look at there's a change of state and there's been a change in temperature. Okay, so these ones came up quite a lot in some different past papers. Okay, so this one says I've got 10 grams of ice and I'm dropping it into a bucket that's got 0.3 kilograms of water. Okay, so for me, I think physics is really difficult without pictures. Okay, so I would, if you get anything from me today, put pictures in there. Okay, so Rosila, just for you, E equals ml. We use that any time that you see that there's a change in state. Okay, so anytime there's a change in state, that's what we use. And anytime there is a change in temperature, that's when we use this one. Okay, so remember, E is what they use in all the other exam boards, but they use Q for energy in AQA. So they just mean the same thing. There's different ways of writing the energy. Okay, so electro, hopefully this one will help you out. So we're going to do another few of these. So hopefully this one will help you out. So try this one. Everyone actually have a go at it yourselves. And as soon as you have a go at it, pop your answer in the chat. But again, for me, physics, I have to have pictures, right? So for me, I would draw a bucket. And it says I've got 0.3 kilograms of water in there. It says we've got ice. So I'm drawing my little bit of ice. It says 10 grams. Straight away I think, nope, I can't use 10 grams. It has to be in kilograms. And it told me that that ice is at negative 12 degrees Celsius. So that's what temperature is. I'm dropping it in the bucket. And the bucket is at 25 degrees Celsius. I'm going to put that in my chat. Or my picture, sorry. No. Here, you don't lose marks. You don't get marks in AQA physics or in any physics for writing equations. You get marks for putting your numbers in the equations in the right place. Yeah, so it's not like GCSE because they give you everything, right? They have a booklet. You have like 7 pages, 5 pages, double-sided. It's because they give you everything. They're not going to give you marks for the equations ever. It's just if you put the numbers in the right place in the equation. Okay, so have a go at this one, see if I can figure it out. So what I'm thinking first is, right, I've got ice here and I'm dropping it in water. And like we said earlier, thermal equilibrium has to happen, right? Both that ice and that water are going to get to the same temperature. So clearly my ice first has to change state and it has to go from a solid into a liquid. It's the first thing that has to happen. So the energy for that to happen, change in state, I always use this equation. So my ice was 0.01 and I'm changing state of my ice. Okay, so then I have to find a word ice. There's 2 ices here. One of them is the specific heat capacity of ice, and one of them is the heat of fusion of ice. So to change state of that ice, I have to do 0.01 times 3.36 times 10 to the power 5. Hopefully you're all thinking though, ice only changes state once it's already at 0 degrees Celsius. Okay, but our ice isn't at 0 degrees Celsius. Our ice is at negative 12. So I have to heat my ice up first. Okay, so the first thing that's happened is I'm heating my ice up. So I know if I'm heating it up, I have to use this equation, right? Because there's a change in temperature. So I'm doing it for my ice. So my mass of my ice is 0.01. The specific heat capacity of my ice is 2100. And the change in temperature is I have to go from negative 12 to 0. Okay, so if you look at this question, it never told you that ice changes state at 0 degrees Celsius. You have to remember that. Okay, so 0 and 100 in numbers, you just need to remember. So I know it's going from negative 12 to 0, so that change in temperature is 12. Once I get my ice all to 0 degrees Celsius, the second thing we just said that happens is that ice is going to change state. So I've got all of my 0.01 kilograms of ice changes state into water. So now what I have is my 0.01 kilograms of water that is at 0 degrees Celsius. And clearly I need to heat that water up now. So I'm going to heat it up to some final temperature, some final equilibrium temperature. Okay. So that third thing then is I'm going to take my water and heat it up to the final equilibrium temperature. So my mass of my water at 0 degrees Celsius is 0.01 times the specific heat capacity of the water is 4200 times the change in temperature. So it's going to be final temperature minus the initial temperature. But because the initial temperature is just 0, we can just ignore that in that math. So it's just to some final temperature that I don't know what that is yet. Okay. Yep, Kitan, come to that now. So remember, right now, my first, second, and third thing are all of these things are increasing temperature. They're all heating up. But like you just said, the water is at 25 and it obviously has to cool down to get to some final temperature. So the fourth thing that's happening here is that I'm cooling something down. I'm taking my 0.3 kilograms of water and I have to cool it down to some final temperature. So that's why I'm going to do E equals my mass of my water times my specific heat capacity of my water times the change in temperature of my water. And this part, I just want you to all look at for a second. We are going to practice this again, okay? The change in temperature, and they always get you out here, has to be a magnitude number, has to be positive. So we know it's going to cool down, right? So we know if I did the final temperature minus the initial temperature, because it cools down, that will give me a negative number, okay? But because we don't want that to happen, you're always going to do magnitudes of it. So that's why you have to figure out it's going to be 25 minus the temperature final that it gets to, okay? So if this one, you're just thinking, I want the magnitude of it, okay? So all we do now is we have to equate this. So remember, this was being heated up, this was being heated up, this was being heated up. So we add them all together and equate them. So when I do my math here, and I typed the numbers in my calculator a second ago, when I do my math here, when you multiply these numbers out, you get 252 joules. When you do your math here for this number, you're going to get a number of 3360 joules. And when you do your math here for this number, you're going to get 42 times some final temperature. And when you do your math here for this number, you're going to get 31500 minus 1260 times some temperature. So hopefully you're thinking now, all I can do is just equate them. So I'm just going to change color for that. So now what I'm going to do is 252 plus 3360 plus 42t must equal 31500 minus 1260t. And hopefully you're thinking from math, I can take all my numbers to one side and all my t's to one side. You'll get a final bit of 27888 equals 1302t. So I just want to get t. I divide both sides by 1302 to get 21.42 degrees Celsius. Okay, so have a quick look at that because we're going to try another one of those anyway. Okay, so have a quick look at it. Okay, so I'm just going to highlight some things and then pop in the chat where you got lost and see if you get the same math as me, okay? So remember the first thing, our ice at negative 12 degrees Celsius. I'm going to change my highlighter. Our ice is at negative 12 and my ice, I know at negative 12 first has to increase in temperature to 0. So the increase in temperature, because it's a change in temperature, I use this equation. So my ice, this mass of my ice, it's currently ice, which is why I have to use the specific heat capacity of ice, times the change temperature of my ice gives me this number. Then I know once my ice has got to 0 degrees Celsius, it has to change state. So we take our ice and do our change in state of our ice to get this number. Then once our ice has changed state, we know that at water that is now at 0 degrees Celsius, my water at 0 degrees Celsius has to increase and my water at 25 degrees Celsius has to decrease. Okay, so we've got two waters now, one at 0 degrees Celsius and one at 25. And one has to lower and one has to increase until they get into equilibrium. Okay, so what's happening here, I've got my water at 0 degrees Celsius, because it's water, I have to increase that to some final temperature. And I have my water at 25 degrees Celsius, has to decrease to some temperature. Okay, and remember this bit, we want to get a positive number, which is why I can't do final minus initial, because I know it drops. I have to do 25 minus TF because I want a magnitude in here, a positive number. Okay, so when we do this math out, you do 0.3 times 4,200 times 25, you do 0.3 times 4,200 times TF, you get this number. Okay, so now what we've done is we've heated the ice up, we've changed temperature of the ice, it's all putting energy in. It's because all of these numbers are putting energy in, all of the energy that I input, I had those all together, and it must equal the energy that came out from cooling that water down. So that's why we can equate both of those parts of math. The energy to heat something up equals the energy for the thing to cool down. We're assuming none's lost in surroundings. So when we equate that, we can take all our numbers to one side and all our t's to one side to figure out what the final temperature reached is. Okay, so like I said, the first half now you're like, well, this is okay, but you have to make sure you're very okay with what change in state is and what change in temperature is, so that you can really think through the different stages that are happening. Okay, so we know there's been a change in temperature of ice because it was still ice, so we changed temperature of the ice. Then we had to change state of the ice, and then once that ice changed state to water at 0 degrees C, we had to increase the temperature of the water. 3 and 4 again. Yes, so remember, once our ice changed state, right, that means that we've got in this beaker right now, I have 0.3 0.01. I just can't, oops. Sorry. Ooh. There we go. Sorry. Technical fault, my bad. I didn't know what I did there. What was I? Get my pen back so I can circle it for you. So what we did here is we've got ice in here, 0.01 of it, but it's at 0 degrees Celsius. Okay. And we need our ice and our water to get to the same temperature. So our ice at 0 degrees Celsius has to increase in temperature. And then 4 was our water at 25 degrees Celsius has to decrease in temperature. So that's what those two are. Yeah, Timothy, this is a question that comes up quite a bit. So this is a past paper question. Well, I just adapted it quite a bit because we can't copy past paper questions, right? So the next one we'll look at now. So that's there. And obviously you can replay this if you want to look at it again. And there's a homework question on this. I know you're probably hearing homework being like, what? But we'll talk about that in a sec as well. So we're going to try another one so you can see another example, right? And I feel like the more we'll do, hopefully you'll get into the swing of it. Okay, so this one. So have a read at it and then we'll draw pictures. Okay, so it says, imagine I've got 200 grams of ice in a bucket that's got 1 kilogram of water, right? So we're doing the same thing here. I'm just giving you different numbers. The ice is initially at -10 and the water is 25. Can you calculate their final equilibrium temperature? And here's the data I've given you. So hopefully you're seeing it's the exact same question as before. We've just changed the numbers. Okay, so if you draw your pictures, what I have here, if I've got my bucket of water, it's 1 kilogram of water, and my water is at 25 degrees Celsius, same as before. I've got my ice, and I've got 200 grams of it, so I've got 0.2 kilograms of ice, and my ice is at -10 degrees Celsius. I'm dropping that in, so what I know needs to happen is my ice first has to increase in temperature to 0 degrees Celsius, then my ice has to change state, and then once my ice changes state to have 0 degrees Celsius water, that 0 degrees Celsius water has to increase in temperature to become in thermal equilibrium with my 1 kilogram of 25 degrees Celsius water. Okay, so see if you can give it a go and pop your answer in the chat. Okay, so remember, you got to take this one slow, separate parts. So step 1, we're thinking, is that my ice has to increase in temperature. So ice is increasing in temperature. So because there's an increase in temperature, I'm using MC, change in temperature. So the mass of my ice is 0.2. I've got to use my specific heat capacity of ice, which is 2100, times the change in temperature of my ice. My temperature ice has to go from -10 to 0 because I know ice changes state at 0. So that's times by 10. And then when I do that math in my calculator and plug those numbers in, because I did it a hot second ago, you get 4200 joules. Second thing that happens is that my ice needs to change state. So as soon as you have the answer, pop in the chat. So when change of state occurs, I know I got to use this equation. So I take my mass of my ice times the change in state of ice, which is 3.36 times 10 to the power 5. When I do that math, I got an answer of 67200 joules. Okay, third thing then is I now have 0.2 kilograms of water because it's just changed state, but it's currently at 0 degrees Celsius, right? Fine, giving it a go, but nope, you're a bit high. So it's 0 degrees Celsius, and I need to increase that to some final temperature. So that's going to be 0.2 times, it's now water, 4200 times some final temperature that it reaches. And we just simplify that a little bit, you get 840 times T. The fourth thing now, because all of those members me increasing the temperature of that ice, or change the state of the ice, is that my water, which was at 25 degrees Celsius, has to cool to some final temperature. So that's a change in state, or change in energy, sorry. So my mass of water is 1 times the specific heat capacity of water times the change in temperature of water. Remember, I can't do final minus initial because that'll give me a negative number and it has to be a magnitude. So because it drops, I'm going to write 25 minus T. So when we solve that math out then, you get 105,000 minus 4200 T. Okay? So now I look at all of my increases and I want to add those together. So I add all of these together and it must equal the energy that was lost. So what I have now is I have my 4200 plus 67200 plus 840 T must equal 105,000 minus 4200T. So remember, what I do is take my numbers all to one side, hit my temperatures all to one side, and you should be left with 33600 equals 5040 times T. Still a bit high with temperature, because think about it, right? I can't get higher than 25. So T, hopefully you then get 6.67 degrees Celsius. Okay, 6.67 degrees Celsius. 6.67 degrees Celsius. Okay, so just because looking at some of your answers there, Carl, I didn't even see it. Ruben, good job. Good on you. That was brilliant. Okay, so this one, again, we just said that this is the year 13 topic you're going to go into if you haven't learned it yet. So you'll do quite a lot of this probably in your classes, but these come up quite a lot in past paper questions. So these are just quite a few adapted ones for me trying to give you loads of different examples. So you just got to do it, make sure you do your math in really slow steps. Right? And the lucky thing about this, right, you can just replay this again and watch it. And there's a homework. So I know you're thinking like summer school, homework, what's she doing? But it's just because this is to give you an idea of what the courses are like through the year. So through the year, every time we do a class, there'll be homework after. So there's just free multiple choice questions on there just to get you practicing the stuff we did today. And then they get self-marked because they're multiple choice. And if you get any wrong, there's a video on there as well. And you can just watch the video and then go to say you got question 3 wrong. You just skipped question 3 and you can watch me talking through the steps of how to do it again. Okay? Yeah, awamatics, like we just said, right? This is like something you just do, repeat over and over again, and then eventually you'll get the math. So you can see that this question we just did and the question prior, they're the exact same question, just to get you into the hang of how to set up the math. Because the thing that everyone gets stuck with is they forget that once the ice changes state, it's now water at 0 degrees Celsius, right? It's not that you now have 1.2 kilograms of water all at the same temperature. You have 0.2 kilograms of water at 0 degrees Celsius, and we have 1 kilogram of water at 25 degrees Celsius. And then they have to become into thermal equilibrium, right? It's not that we've just ended up with 1.2 kilograms of water all at 25. We've got the one at 0 degrees Celsius and the one at 25, and then they come in thermal equilibrium with each other. Okay? Okay, so for some of you that may be a little bit tense, but hopefully I'll see you on Thursday, and we're going to practice this stuff again at the start, and then we're going to go a bit more into the gas laws. So we're doing gas laws on Thursday. Okay, so again, if you've done this in school already, hopefully this is getting you ready for what's coming up, because you're just revising it and you're going to new topics, or maybe you haven't done it before. Yeah, Carla, yeah, so what summer school is for is just to show you exactly what our courses will be like all through the year. So the way that I'm teaching summer school is exactly how they'll be done for year 13. So yeah, so like Garrick said, so Garrick is helping us out today. So there'll be someone, hopefully Garrick, other people maybe, other past students will be in. So Garrick's someone I used to teach. There'll be people like helping you out. If I can't get to your questions, someone else in the chat will hopefully help you out. And you all just be helping each other a little bit as well, which is quite nice. Yeah, so the last question in the workbook, I just didn't want to smash to it, but if you had to go with the last question in the workbook, I'll just put the answer up. The mass is 5.58 grams. And on Thursday, we can go over that one again, okay? Because there's no point us rushing through. So on Thursday, we can do this one again. So I'll just, at the end of Thursday, we can pull this up. So we'll do Thursday's lesson, and if we go through it fine, we'll pull this one up on Thursday to finish off. Okay? Put your personal statement you went to summer school. I'm not going to lie, it probably looks really good that you went to summer school, right? Because you'll be like, what? They're going to ask, what did you guys have in the classroom? And you could talk about the people you met as well. Okay, so that was intense hour. Thank you for all of you asking questions in the chat, right? Because that's what helps me to know where to pause. Okay, so yeah, so Thursday, Thursday's the next lesson. Isn't that right? Did I say something wrong? Now you're making me doubt myself. Yeah, so Thursday, same time. Yeah, 2 to 3. Yeah, Thursday, same time, we're going to do the gas laws, and we'll go over a bit more of this. Kitan, can you send me like a quick message on TikTok? If you have me on TikTok, it's just what it was at the start there, and I can send you a link so you can see the prices if that helps you out. Because there's like different prices for different parts of the courses. But again, it's all set up so it's much cheaper than a personal tutor. Okay. Right. Have a lovely day. Hopefully I'll see you guys on Thursday. Yes. And remember, you can just play this back if you want to go over those questions again. So it was lovely to meet y'all, and I'll see you Thursday. Key stage 3 physics. Yeah, that's where I'm going now. Bye, guys.